Alright, this is Chapter 21, Problem 6, which says this. A fixed 10.8 centimeter diameter wire coil is perpendicular to a magnetic field which is 0.48 Tesla pointing up. In 0.16 seconds, the field is changed to 0.25 Tesla pointing down. What is the average induced EMF in the coil? So let's draw a couple of pictures. Let's draw two pictures from the side. So the coil, imagine it's sort of laying on its side and it has a certain diameter d. And the magnetic field is at the moment pointing up, and it has a magnitude of 0.48 Tesla. And this is from the side. And then, so later, this is 0.16 seconds later, the coil is in the same spot. Magnetic field strength, though, is pointing down, and now it has a strength of 0.25 Tesla. All right, and we're supposed to figure out what is the average induced EMF in the coil. So look, to do this, what we have to remember is that there's a formula for computing the induced EMF in a coil that involves how the magnetic flux changes through the coil as a function of time. And that is Faraday's law of induction. The EMF, squiggly E, is given by minus, and then the change in the magnetic flux divided by the change in time over which that occurs. And technically, one might even put an N here, where N is equal to the number of coils, a number of loops, but if there's only one loop in this case, so N equals 1 for us. Okay. In fact, as long as we're figuring out what variables we have N equal to 1, we have delta T equal to 0.16 seconds, and some other things are indicated. They give us that little d, the diameter, is equal to 10.8 centimeters, which we might as well go ahead and write the radius, which is half of that, or 5.4 centimeters, which is also 0.054 meters. Okay. It will be helpful for us to then compute or figure out what the formula is for magnetic flux. So recall, magnetic flux involves the strength of the magnetic field, the area, and the cosine of theta, where again theta is the angle between the magnetic field direction and the direction that is normal to the area itself. And so that's probably worth drawing here. I'm going to go ahead and just sort of call this the area vector. It points normal to the area of the coil. So I'll call this like that. Okay. And when I write B and when I write A, these are just simply magnitudes. So just keeping that in mind. Magnitude of B. Okay, so so far so good. What we need to do apparently is calculate the area. So that is not bad. I'll write that down. The formula involves, well, it's pi times the radius squared, and so that will be pi times 0.054 meters squared. I'll put in the details in a bit. The angle theta, so in fact if we look at what's going on, at first the magnetic field is completely aligned with the area vector, and so I'll write theta initial, I'll put that over here, theta initial is 0 degrees. In the end the magnetic field is pointing down, and so in the end the angle there is 180 degrees, theta final. The area is the same. The magnetic field strength is changing. So now what we're ready to do is determine the change in the magnetic flux, delta phi b. That's, of course, phi b final minus phi b initial, which involves the final magnetic field strength, the final area, which is the same as the initial area, and cosine of the final angle. That's the 180 degrees, and minus the initial and the area, and cosine of the initial. Cosine of 180 degrees is minus 1. Cosine of 0 degrees is 1. So let me just note that here. This term is minus 1. This term is simply 1. the A's are common, and so I can factor out an A. I'll do that. And in fact, I'll factor out a -1 as well. -1. There are two minuses, if you like. That's what gives me the minus. And so what I'm left with on the inside is B final plus B initial. These are the two magnitudes added together. And so what we have when we start plugging in these numbers, this, if you put in B final of 0.25, B initial 0.48, and you stick in this area, the overall change in the flux is a minus 0.00669 and has the units of meters squared times Tesla. And finally, we're ready to actually compute our EMF. So the EMF, which involves n is equal to 1, we have a minus, and then the change in phi b, which is minus 0.00669 meters squared times Tesla, divided by the time over which the magnetic field changes its direction, 0.16 seconds. Those minus signs cancel, and what we end up with is 4.18 times 10 to the minus 2 volts, and this is 3 sig figs. We should really only take this to 2 sig figs. We're limited, if you like. The magnetic field strengths are given to 2 sig figs, so is the time, and so this should get rounded up to 4.2 times 10 to the minus 2 volts for your EMF. And that is the final answer.